Hi. This is not the part of the curriculum, but it's good to have a lecture like this, just to tie everything you did over Calc 1 and Calc 2 together regarding integration in one spot. So we start from the idea that the integral is the antiderivative. So if we take the derivative of x squared, we get 2x, which means that the antiderivative of 2x dx will be this x squared, and we put plus c because if there was any kind of constant with x squared with the derivative, it would be wiped out, so we don't know. We have to put this plus c. And these are called indefinite integrals. Now, the ones that we care more about are the ones from Riemann Sum, which are definite integrals, and those are the ones with limits. So the Riemann Sum said that limit of the sum of f of xi delta x when I goes from 1 to n and n shoots to infinity was equal to the integral a to b of f of x dx. And from this formula, from Riemann Sum, we learn that integration calculates accumulation because it adds more and more and more. Now, the picture that we associated with this was we took the area under the curve and we calculated these rectangles which all added to the area under the curve. Now, at first, because it's very crude, we have a lot of error. And then as we make these rectangles thinner and thinner and thinner by putting in more and more of those, the area becomes better and better and better. So this is happening between A and B. And then I'm going to just color one of these, and I'm going to call, I could have colored any of them. I just colored this one. And I'm going to call this one representative dx rectangle. Now, when I draw dx to set up the integral, and I draw that vertical thick line, I'm actually drawing one representative rectangle from all these rectangles that are there. So now, as you can see, this representative rectangle is touching a function f of x on top, and it's sitting on the x-axis on the bottom. So now, if I want to calculate the area, I can calculate that by simply taking the f of x dx from A to B. And I can upgrade that to area between two curves. If I have two functions, they don't have to intersect, these ones do, where I have f and g, two different functions, and now, here I am, I drew one of these dx representative rectangles. Now, why do I draw a representative rectangle? Because it helps me set up integral. When I draw, when I say area equals, and I draw integral sign, A to B, I look at my representative rectangle, and I can see that the top of the representative rectangle is always on F, and the bottom is always on G, so it becomes F minus G dx. So this representative rectangle is stuck between two functions. And that's why I like it. Now also, I know that when I draw a representative rectangle like this, is a dx, and when I draw a representative rectangle like this, is dy. So we already took a basic idea from Calculus 1, where integration calculates accumulation, and we used it to find area under the curve. But that's the still area between two curves, because the top curve is the function and the bottom curve is x-axis, which is y equal to 0. So this is your y equals 0 line on the bottom and y equals f of x on the top. So you could write your area formula here as f of x minus 0, which would look exactly the same as this one, because that's what it is. It's area between two curves, where the top curve is a function and the bottom curve is x-axis. So if I have two functions, I can use the formula on the bottom. If I have only one function, I use the formula on top, but technically formula on the top is the formula on the bottom when g is 0, y equals 0, right, x-axis. So from here, I say, what else can I do? If I have a function of some kind, yeah, which is f of x, I can rotate that function around x-axis, and I can create a shape that is circular in a base, like a vase or your bottles of water or cups of coffee, so anything that it's round. And for those types of objects, we can calculate volume, and we can calculate surface area, which is what we calculated today. So we write down formulas. We have, well, let's go disk first. We have disk method, which is if you have only one function, right, and the whole object is just a solid block, right? The disk volume would be pi integral a to b of, and then you just say f of x squared dx. Now you would say, is this something that would give me the volume? Sure, right? Because first off, what you have here, as I said in the class the day when we did this method, I said your area, the volume is base times the height. And your base is area is pi r squared. So you already see pi r squared in your integral formula, and here is your times the height, because this the location from A to B is actually your length. But if you have the rotational object, which is rotated on x-axis standing horizontal, right? When you stand it up, this length from A and B becomes its height, and the circle on the bottom becomes the base. So the volume is area of the base times the height. That's always the case for volume. Area of the base times the height. So if I create the object by having it horizontal, when I rotate around x-axis, when I stand it up, you see the same A to B, which was on the x-axis, now becomes the height of the object. So now in the formula, I have area of the base, which is fx squared pi, that's the area of the base, times the height, which is the dx. So this formula makes sense to be a volume formula because I have the area of the base times the height. Another way is to count dimensions and analyze this disk method to see that it is a three-dimensional formula. You have 2 dimensions here times 1 dimension here, so altogether 3 dimensions, and volume is 3-dimensional. So we have we came to the point where we rotate a function around x-axis and we create volume. Now, the same jump that we have here from area under the curve, upgrading to area between two curves, we can do the same upgrade for our rotation. Because if I rotate 2 curves, then I will rotate. So if I rotate 2 curves, F and G, again, here's my representative rectangle, between A and B, and we're rotating on x-axis again. Now, we call this washer method. The volume is pi integral AB, and now you have F squared minus G squared, all of that dx. So the upgrade is the same as what we had. And now why is the same? Well, it's the same because now you're taking area between two curves and rotating that. So you still have f minus g, but now you have f squared minus g squared because we have rotation, right? And we have r squared. So you are taking this area and you rotate around, you will get this round object with a kind of conical cut inside, and there will be a hole on this end and a much bigger hole on the other end, right? So the object will be round, but it will have a hole on the bottom and a bigger hole on the top when you stand this up. So the upgrade went from having a single function up there with a single function in disk method to having two functions now, area between them, and then. Now, again, look at the representative rectangle. It stretches between f and g, and f is on the top, g is on the bottom, so we have f squared minus g squared. There's also shell method, but it doesn't really factor into this story, so there is a shell method. Now we move to length of curve, so we are now going back, and we are going all the way back. So we did area, we did volume, now we're going back to length. So we go back to length, and we take some curve, I don't know, square root of x, let's say. I'll just put f of x over here. And we can calculate the length. We did this for last two classes. As integral a to b of square root of 1 plus f prime squared of x dx. I derived this formula in the class. And I also explained earlier today why is this one-dimensional, right? The square cancels the root, and then derivative cancels the integral, and all you have left is just f of x floating about. So that's one-dimensional, right? So we can calculate lengths of curves using these integrals. And finally, now, if you take the same function and you rotate that function around x-axis, you will get the surface area of revolution. Don't forget the 2 pi of AB, square root of 1 plus f prime squared of x. Oh, I forgot f of x here. Oops. Dx. There is f of x in front of that square root. And now the whole story is complete. This is where we end upgrades in Calc 2. What else you get to do with this? Later, polar coordinates, and then jump into 3D with Calc 3, and then use polar coordinates, cylindrical coordinates, spherical coordinates, and all other methods to calculate volume, and even the 4-dimensional ideas where we talk about distribution of temperature or whatever, density in the object, that it's perfectly bound by the 3 integrals on the sides. So this is all of integration, and we'll use this, obviously. There are some other tricks that we would eventually have to discuss, so maybe next class, in terms of how to set up things, and but you know, this progression is important. So there's the story of integration.
Nope.
See you in 2 days.